Look closely at this simple shape. We recognize it instantly, but what actually makes a circle a circle? If you ask a child, you'll probably get an intuitive answer. They might point to a clock on the wall and say, it's round. Or they might trace the edge of a coin and point out that it has no corners. And they're right. A pizza, a coin, a clock face, our eyes group these objects together because they share a common physical profile. But human perception is notoriously fuzzy. Relying on roundness works for ordering lunch, but mathematics demands rigid precision. To guarantee that you and I are describing the exact same universal rules, we have to establish a strict definition. Here is the standard rulebook you'll find in any middle school geometry text. A circle is the set of all points in a plane that sit at the exact same distance, the radius, from a single fixed center point. We can translate that geometric rule directly into Cartesian algebra. Using the Pythagorean theorem to measure the x and y coordinates on a grid, we map the entire boundary. X squared plus y squared equals the radius squared. But look closely at the words we use to build that baseline. There are strict constraints holding this shape together, specifically the phrases in a plane and fixed center point. Mathematical definitions are actually fragile sets of rules. If we delete just one of those foundational constraints, the shape we think we know transforms into something else entirely. Let's cross out the phrase in a plane. Instantly, we are asking for all points at a set distance from a center, but now we're looking in three-dimensional space. The circle itself expands into a sphere. This new space gives us two distinct ways to draw a circle on its surface. If you cut directly through the center of the sphere, the rim of that slice shares the exact same radius as the sphere itself. This is a great circle. But move the slice up or down so it misses that center point, and the resulting rim shrinks. We now have a small circle. You already use this geometry to navigate the real world. The equator is a great circle, tracing the widest possible path around the Earth. Every other line of latitude above or below it is a small circle. A circle's identity is entirely dependent on the spatial dimension it inhabits. Changing space literally bends the rules of what the boundary can be. Let's return to a flat, two-dimensional plane. This time, we delete the fixed center rule. This setup comes from the Greek mathematician Apollonius. We lock down points A and B. Then we place a third floating point, P. The rule is simple. The distance from P to A divided by the distance from P to B must equal a specific constant, K. If we set that ratio equal to 1, meaning P is equidistant from both A and B, the path of all possible locations for P forms a straight perpendicular dividing line. No curves in sight. Now introduce some tension. Change the rule so the distance to A is exactly twice the distance to B. With an uneven ratio, that straight line immediately collapses. If you plot every single location on the board that satisfies this 2-to-1 ratio, the points snap together to form a perfectly round loop. This is the Apollonius circle. The geometry inside this loop works, because if you draw lines bisecting the angles from the outer boundary, they will always strike two highly predictable division points on the baseline between A and B. It proves a circle doesn't actually need a singular center point to exist. It can be born entirely from the mathematical push and pull of a ratio between two competing locations. There is one final invisible rule dictating how we draw shapes: the square, horizontal, and vertical language of the Cartesian grid itself. Instead of x and y, we can map space using polar coordinates. Location is defined by distance from a pole, radius r, and an angle, theta. This simplifies the math. R equals r. Lock that radius, sweep 360 degrees, and the shape draws itself. Without the angle in the equation, polar language proves rotational symmetry. Spin the shape infinitely, the math doesn't change. Pushing further, if we make radius a function of the angle, say 1 plus cosine theta, the circle caves inward, forming new geometric cousins, like the cardioid. This is the native mathematical language of cosmic physics. Planetary orbits use a variation of this exact same polar formula, just with a measure of eccentricity added to stretch the boundary. Shifting how we describe a shape across dimensions, ratios, and coordinate systems provides the specific vocabulary needed to map the physical world. These mathematical frameworks expose the structural patterns found throughout the universe.